theory side. And so it's my pleasure to introduce Dr. Jorgen Randrup. So he got his PhD in theoretical physics from University of Aarhus, I don't know if I pronounce right, in Denmark. He was a postdoc at Lawrence Lab in Berkeley and the Niels Bohr Institute in Copenhagen. And since then he has been at Lawrence Berkeley Laboratory. He has worked primarily on nuclear collision dynamics over a wide energy range, from damped nuclear reactions and multi-fragmentation to ultra-relativistic heavy ion collisions. And for the past dozen years, he has concentrated on fission, where he has introduced a Brownian shape evolution treatment of fission dynamics, and with Ramonavov, he has developed the fission simulation called FRIA. Okay? And
thank you very much.
one tidbit of information: when I first arrived in the US, my first scientific visit, was actually in your group, in the theory group at Berkeley.
Yes.
Thanks also to Nikolai.
Yeah, you came as a student of Nikolai, who was there, yes. Can you hear me? Is this on? Good. All right, so good morning, everybody. I have been asked to speak about what neutrons and photons are good for, so to speak, observables that can help us learn something about fission. And so you all know by now, you should, fission, the nucleus splits in two. You get two excited fragments, they move apart due to the Coulomb repulsion, they have angular momentum, they have excitation, and they ultimately emit neutrons and photons, right? So I divide this up in first a little bit of an overview, although you have seen them a lot, but now you get my overview of fission, which has the advantage that you somehow different stages time-wise. And then I will talk about the fission neutrons, and then I'll talk about the photons. And for those of you who have sort of questions that require more of an extended discussion or want something clarified, I thought I would arrange some office hour afterwards over at the bagel stop. So you can come over there with me and we can talk more about it, have the time. That depends on... Exactly. All right, so stages of fission, right? What we most talk about is induced fission. So you have a cold nucleus, it's blue because it's cold. You shoot something at it after the neutron. Then it gets excited and it can establish equilibrium. Maybe there's pre-equilibrium processes first. Sooner or later you have a compound nucleus, which then undergoes some very complicated shape evolution, which is really where my heart lies. The shape evolves in some way, and finally you go over the barrier, you come down into the scission configuration where the system splits. And then, in a sense, fission is over. But you get the two fragments, I said, they move apart and ultimately decay, and this is what we're going to talk most about today. You could also have a spontaneous fission. There the beginning is simpler, you don't have to do anything but wait, and then the nucleus from its ground state tunnels through the barrier and then proceeds in a similar way in some diffusive manner down to the scission, and the system splits. This has not been, here is a lot of still work to do. There are some progress, but we understand, I think, much better about over here what is going on. Now, let me just say a little bit about the shape evolution, because it will come in later, some things. The way you should think about this shape evolution is that it's kind of a highly dissipative process. This is also what Orell said he finds with his microscopic calculation. The dissipation is strong. So the shape is very much like a Brownian particle that interacts with the rest of the system, and therefore you can simulate the whole thing as a random walk among the shapes. And of course, in a random walk, it's random, but there are still probabilities, and the probabilities are such that the weight of a particular shape is simply proportional to how many states are available at that shape. So for example, if you're here at the top of the barrier, this elongated one, you don't have so many states available as if you are here at the minimum, right? So then you have a random walk defined, and you can do it. And this goes all the way down to scission. This will be important later. Now, because it is such a random walk, many things can happen, and you also don't get just one scission shape, you get many. So even for the same mass partition, you get a compact scission shape, an elongated scission shape, they give different kinetic energies and so on, and you can get different mass splits and so on and so forth, right? So you get the whole slew of things in such an approach. So it's not deterministic, it is stochastic. Let us see what happened here. All right. So therefore, somehow one can say from 1 to 2 is the main fission. And I have this Latin term here, some of you will recognize, ex uno plurus. It's a little bit the inverse of what the American motto is, I think, but maybe it's more appropriate. So here is finally what we're going to talk about, the further fate of the fragments after you have split. So the fragment is excited, statistically it has rotation. And there is a certain sequence to it. We have first the prompt processes, that's neutrons out, photons out, pretty much like that. Somebody asked about why not photons first or something. And it's a matter of probabilities, as Keegan said. I think it's natural that the strongly interacting particles come first, then the electromagnetic interacting, and then the weak interactions. This is somehow how it goes. It's a matter of phase space to some extent, but this is an electromagnetic interaction. It's a lot weaker than the strong interaction. So it is natural that in the beginning the neutrons dominate, but as you begin to run low on energy for the neutrons, the photons can come in and compete. And sometimes we get photons with very large energy. That I'm not going to talk about. So it comes here, it comes down to the so-called prompt product nucleus, and I'm not going to go any further, but in reality these all have too many neutrons, of course, because they come from a heavy nucleus, so they will beta decay, and subsequently you will get this thing repeated after each beta decay, then you come down to the so-called cumulative product nucleus. All right, so here is the 2 parts I will do. We will take a short break after the neutrons, and I then looked up at Wikipedia what is a neutron. That's good to know if you're going to talk about it. It's a hadron and it's a fermion. This is important. It satisfies Fermi-Dirac statistics. So in the nucleus you have a gas of nucleons. They are filled up to the Fermi surface. So it's subject to the strong interaction, not to the electromagnetic interaction, because there's 0 charge, it has a mass about 1 GeV, and it has a spin. That's also important. You know all these things. So now you can get neutrons in many ways in fission, and this is quite confusing from the experimental point of view. So first you have this very excited, let's just say compound nucleus, but if it's excited enough it could emit a neutron and then fission, or another neutron and then fission. So you get not just the first chance to fission, you get second chance and so on, as you heard about multi-chance fission. So neutrons can come from here. Those neutrons, they are kind of centered kinematically around the compound nucleus. This means centered around the lab, let us say. In contrast to those emitted from the fragments later, they are from a moving source. So there is some difference between them. Now, the next time you get an important source of neutrons is just at scission. Scission is very poorly understood, and there is increasing belief that there could be some neutrons emitted occasionally here. They're called the fission neutrons. We heard about it the previous days. I will not talk about this either, but I will talk about the fissions that come from the accelerated primary fragments. They are the most important ones. And typically, such a fission fragment emits 1 or 2 neutrons. Okay. So let us just look at the neutron evaporation process first before we start talking about what we can use the neutrons for. So before we have the mother nucleus, so to speak, and then after we have the daughter nucleus and the neutron running, and they move oppositely. There's a small recoil for this to move slowly, so slowly that its kinetic energy is practically negligible. And now let's do the energetics first. This is common to all treatments of neutron evaporation. So you have the excited mother nucleus, the ground state, and excitation. It sits at rest, and then you have a similar thing for the daughter. It's moving with the kinetic energy, and most of the kinetic energy sits in the neutron because it's so light. So this is kinematics, and you have the energy balance. The initial energy has to go to the excitation energy of the daughter, the mass of the neutron, and the kinetic energy of the 2 final particles. So Q value is the difference in these masses, and this is the energy you can share between excitation energy in the daughter and kinetic energy of the neutron. And you know, if you were to emit a neutron at 0 energy, then you would get the maximum possible excitation energy in the daughter. So this is one way to define the Q value. Or if you put as much energy as you could into the neutron and left with a cold daughter, that's also the Q value, right? So that's the important quantity, and the question is, and then the final thing is, you have a separation energy because the neutron is bound here and it costs energy to lift it up. And this is the neutron separation energy. For the actinides, it's sort of 6 MeV around that, and in the fragments it's maybe a little less, 5 MeV or something like that. So this is a cost you have to pay every time you emit a neutron. So here's a diagram with the energies, the excitation energy, the mother, how you have first to pay the separation energy, and then you have the Q value you can split between the daughter and the neutron. And the whole question is, where does this dividing line go, right? This tells you if it's far down, then you have a lot of energy in the neutron and so on. So what is the distribution of the dividing line? That's the energy spectrum, the prompt, what's called neutron spectrum, right? And Keegan showed this figure here, experimental attempts to measure this, how it was originally like this. The most recent ones, it looks like this. So let us see, what would you expect by just some simple considerations for the neutrons. And when I started with Ramona to develop fire, I was faced with having to put in neutron evaporation, which I didn't know anything about. So I thought, well, I just think about black body radiation. So I think about the excited nucleus as having a Fermi gas of neutrons, and they can then boil off essentially, as Keegan was saying. So let us try to do that. Here's the energy diagram again, with the various quantities of interest and the maximum temperature you can have in the daughter. That means because most of the energy goes in the daughter, so you're sitting up here somewhere. So now, when you do that, you get a very simple formula. But there is a difference between this formula and what Keegan showed. So there are 3 factors in this formula. First, there is the occupancy in the compound nucleus. You have a Fermi-Dirac distribution, but you're way about the Fermi level, so it's like a Maxwellian distribution, e to the minus energy over essentially the maximum temperature there, right? And then you have the phase space for the neutron, the kinematic phase space, like this. You have square root E dE and the angular thing. But then what was not in Keegan's formula is the fact that if you have these neutrons or particles in there, they want to boil off, those that move fast towards the surface, they come out sooner than those that move slow towards the surface. So you have an extra factor, an extra modulation of a velocity, which is a square root of the kinetic energy. This biases, the spectrum towards higher energy is tilted. So you have this one. So in the end, you get a factor of energy here and not square root of energy. This affects the shape. So let's see now what this gives. So it's obviously isotropic. Generally speaking, these neutrons evaporate in an isotropic way. There is a small effect. If you rotate, it flattens a little bit, but it's not very big. And the spectrum I mentioned is an energy times the exponential. And then also the cooling, we mentioned every time you emit a neutron, the average excitation energy goes down by the separation energy and the temperature in the system. Like the average of the kinetic energy here is the temperature. So let us see then. Here is the experimental data. Now let's put on what just some simple black body radiation gives. It looks like this. So this is what we use, okay? This seems to be good enough. Or one could say, some of my theorist friends would say, this means the experiment must be right. Right. So anyway, this is neutron evaporation. Let's ask a few elementary questions. So the neutron takes away some energy, so it means some momentum. Yeah? Yes? What was it? Oh.
Yeah, so this fit is really very nice here.
It's not a fit.
Well, presumably it's a fit to...
It's not a fit. It's not a fit. It's to do the calculation I just explained. I just put it on this plot. One thing has been fitted, the normalization, because Keegan's it's unnormalized, right, as he told me.
But so the temperature, how is that chosen? Wasn't the temperature a parameter of the distribution that you had?
Yeah, but this is a specific case. What is this, uranium or something like this? Or what? Yeah. So you do uranium, thermal fission of uranium. I think I had it on here somewhere. Oh, what am I doing here? Where is it? Is it written here? No. But this is your thermal fission of uranium. So all the energetics is given what it is. So just to calculate. Right? Just calculate, nothing. Just no parameters. You know, there are no parameters to put in. I mean, you need to know, of course, where are we? I'm going a little here. You need to know certain things, but you have to calculate those in some model. What is the separation energy, for example, and so on. What is the separation energy, right? That you have to rely on. There are models for that. Take the separation energy, is pretty well established, and you put it in, and you get this.
Okay.
So, so as I said, the norm, because the integral, in my world, the norm of the spectrum should be equal to the multiplicity. But in other people's world, it should be 1. Okay, so anyway, so it's adjusted like this, but we get the right multiplicity, so that's okay. Anyway, now, linear, so that takes care of the linear momentum the neutron takes out. What about the angular momentum? Of course, it takes away some, certainly it has a spin of a half, that counts for something, and then it has an orbital angular momentum somehow. Let's look a little bit at it. It comes out, the normal velocity is slowed down because it has to overcome the potential there, and then it has a perpendicular velocity, and it's basically the cross product is, you know, the radius of the nucleus times the perpendicular momentum there, right? That's the angular momentum. And we can easily sort of estimate this, the radius about 6 Fermi. Now, to get out, the energy of the neutron must be above the step. That means, at that high energy, you're way above the Fermi surface, and the average transverse energy is just the temperature. So this means you can calculate what the average momentum is, becomes 43 MeV/c. You multiply the two together, and you find out how much angular momentum that amounts to, 1.3 units, okay, in the orbital. Then you have to add the half in some way, and you get some kind of typically what the neutron carries out, what you would think. And you should remember that the direction of this is random. The neutron can go one way, neutron can go the other way, irrespective of how the nucleus is rotating. It rotates very slowly. So this means sometimes you add angular momentum, sometimes you subtract angular momentum. So the net effect overall is not expected to be all that big on the nuclear, on the fragment angular momentum. This is an advantage when you come to the gammas, because then the gammas can help you tell what the angular momentum was. And so let us see now. Here's then the calculation where I use the FIRE. FIRE is an event simulator, so it can tell us a bit how things go. So first, this is where you lie in terms of angular momentum and excitation energy just when the fragments are born. Here in the middle you sit here, then you do the evaporation and you come down, and you get then a cold nucleus, or not cold, but it can no longer send neutrons out, and you get a new distribution here. You showed something, somebody showed something like this, and what you should notice is that the mean value doesn't change all that much, as I was just saying. The neutrons don't take very much angular momentum out, typically. Yeah?
There's a question.
Oh, okay.
Yeah, I'm wondering, because when you calculate the angular momentum, you take like a circle, a spherical, but we know the fragments are deformed.
Yeah. This is an estimate. I'll just give you an estimate.
But will it change a lot if you have like a really deformed?
Well, some places they'll be larger, right? Other places it'll be shorter. Mm-hmm. So you know, on the average, I don't know. It will not change it very much. It's just to give you. It's not like 5 or 10 or something like this, right? It's just sort of not very much. Okay. But you're right. I mean, this certainly can be improved, and if you have a deformed nucleus, that's correct. But since it's not so super important, it's I'm not trying to advocate. I just try to give you a feeling for the situation. Okay, now this I will skip quickly over. It's not just you measure neutrons, and in a given event you measure n neutrons, so you get a multiplicity distribution. The one you can really measure is just any neutron. They can come from both fragments. They come, of course, from one fragment or from the other fragment, so you can calculate this in your model, but you cannot really measure it so well. So you get a distribution, or you can characterize by mean and variance and so on, and you can do factorial moments. We heard about this. Just the one thing I want to mention is that the variance is generally smaller than the mean. This means this is not a Poisson distribution at all. Right, and this comes from the fact that there's a cost for each neutron with the separation energy. Then it becomes narrower than the Poisson distribution. Now, what I would like to talk about, so there's one more thing I want to say. This was also mentioned. There is an inverse relation between the kinetic energy of the fragments and the number of neutrons you get out. This is because you have only a certain amount of energy available. So if some of it goes into kinetic energy, you don't have that for statistical energy, and then you don't get so many neutrons. Here's again a calculation. Well, so yeah, this is illustrated here. A compact Fission configuration gives high TKE, low excitation, therefore low multiplicity, and vice versa for the elongated. And here's some calculation where you calculate for different incoming energies. You do thermal 4 up to 14, and you can see, of course, the more energy you put in, more it goes up. But you see here how high neutron multiplicity, you cannot have very much kinetic energy, and vice versa. So these things have to match together, and this puts some constraints on models. Now, what I want to talk a bit about is angular distributions of the neutron and then correlations between the neutrons. Also something that was touched upon. And let's see, where does this one come? Yeah, I want to now give you a pictorial impression of where the neutrons are sort of in velocity space, because I find it very helpful. And one thing, so I want to make a kind of a contour diagram. The emission of the neutrons is approximately isotropic in the frame of the light or heavy fragment. So therefore the contours become spheres, right, around the fragment velocity. So let me try to draw it here. This is supposed to then be velocity space. The light fragment is moving this way. Here sits the compound nucleus at 0. The light sits here, we put this to be the z-axis, then the transverse is this way. So here sits this, and then neutrons are emitted from here, so you get spheres around here. And one thing now, this one here should have come, that it is such, the energies is such that the mean neutron velocity is approximately the same as a typical fragment velocity. So they are sort of the same size. So here are a couple of examples of contours. So low energy neutrons, the red one here, will sit inside this one, and then medium energy like this, and high energy neutrons sit like this in this diagram. And then they'll have a similar one from the other one. And now I put this together and try to show you, to get some, this is made on the computer, very simple thing. What you see here is from the projectile light, here's from the top, or I call heavy fragment, light fragment. And this is, for illustration, I put in a neutron with 14 MeV, and I just look at what happens to the first neutron here. It looks like this. But of course, you can make, just one moment. But you can make several neutrons, multiple, what's called multi-chance fission. So if you do that, then you get some of these pre-fission neutrons on top of it. And you can maybe see that it gets fatter down here because they all are centered around here. So you get sort of more here. So this is how it looks in velocity space. Yes?
On the previous slide, you say approximately, to which extent?
I'm sorry, what?
You say approximately isotropic.
Yeah, well, I said before that if the nucleus rotates, then there's a very slight flattening of the spectrum, right? Because the neutrons, I mean, they go a little bit more to the equatorial direction and to the polar direction. But it is a very small effect, below 1% in the shape. So it's nothing that's worth worrying about today. So now you can begin to see the challenges and opportunities here if you want to measure correlations of neutrons. You can see that if you're interested, for example, in neutrons from the light fragment, then you'd better put your detector so you look in the forward direction, right? And if you look in the forward direction, you're more likely to pick up neutrons from the light fragment and vice versa down here. So in this way, taking advantage of this kinematic feature, you can actually find out the average number of neutrons from the light fragment and from the heavy fragment. You can't do it event by event, but on average you can do it. So that is an advantage. And if you are interested in, let's say, pre-fission neutrons or scission neutrons for that matter, you could try to subtract this sphere that comes from the light and this sphere here, and then see what is left, if there's anything. So you can play with this in various ways. And this I just said. So now the angular distribution of the neutron with respect to the direction of the fragment. This is also a kind of correlation, you could say. I mentioned how they're focused in different directions, and you get then the angular distribution like this. So the heavy fragment, they are focused in the backwards direction. From the light fragment are focused in the forward direction, and if you add them up, you get this over here on the right, some kind of U-shape, but it's a skew U-shape because it turns out you get more neutrons from the light than from the heavy, usually. So therefore you get bigger peak here, and this is compared with some old data, looks quite reasonable. Right. So this is but such a curve here is quite sensitive to how many neutrons come from one and how many come from the other. So this is calculated observable you can use to check your models on how this distribution is. And if you do it fragmentation by fragmentation, it'll be quite different, as we will see later, because in some cases there's more energy in the light fragment, otherwise there's less energy, and then the curve will shift around. So here's a good opportunity for consistency checks. And one could ask, as these people did, is there any room for scission neutrons? And they found at most 10%, but possibly room for scission neutrons. This is a very strong relevance nowadays. This is becoming a hot topic, so to speak. Now, the direction of one neutron relative to the direction of another neutron, that's a little more of a difficult beast. You need to measure two neutrons, but never mind the fission direction. So you have the two neutrons, they have directions, you get the relative angle like this, and now you ask what's the distribution of that. And now if you look again here, you can sort of see that if both neutrons come from the light fragment, they come out here, so the angle can't be too big. Vice versa, they couldn't be too big if they both come from the heavy, but if one comes from the light, the other from the heavy, then they're closer to 180, it'll be big, right? So this is what you can expect, and here it's illustrated with actual calculation. The point is if you get one from the light, one from the heavy, and then you peak at 180, and the ones that come from the same fragment, they are peaked at 0, and of course the light one is bigger because you have more neutrons from there, so you also have more pairs from there, right? And then if you add it all up with the right weights for this thermal fission on plutonium-239, you get some sort of modulation here, kind of a U-shape in the angular distribution there. And this is also then, of course, very sensitive to how many come from one and how many come from the other. And it's also sensitive to the energy of the neutrons. These features show up much better for high energy neutrons than for low energy neutrons. This is kind of clear. When you're close to here, there's not much angular direction, right? So you can kind of see this here, that as you go up in energy, it becomes a stronger and stronger U-shape. So here's another thing you can measure and try to test models with. Here is an attempt to compare with some data over here, and over here even more data with energy dependence. And you can see that one can pretty reasonably understand the observed things, you know, on the basis of this kind of simple kinematic features. All right, now let me see. What I would like to now say something about is how the neutron multiplicity is related to the excitation energy of the fragments when they are formed, and what good that is. So we saw already that each neutron takes out a certain amount of excitation from the nucleus. So therefore, by dividing over, as Keegan showed, you can make a rough estimate how many neutrons you expect. It's probably less proportional to how much excitation energy you had, right? So you can, of course, do better if you have an actual model. So here is just to give you an example again run with a fire event simulator that takes into account that all the different fragments have different separation energy, each particular emission have a different temperature and all of this. Average over all of this. Then you can see this correlates that if you have so much excitation energy in the initial fragment, you get so many evaporated neutrons out. So you can see how close the correlation is. These are not calculational error bars, this is the width of the distribution, right? The variance of the distribution. And conversely, if you measure the number of evaporated neutrons, which is more like what you do, then you could try to deduce back what could the excitation energy in the fragment have been. And you can see it goes like this, right? So we're going to use that. You measure the neutrons and then you use this to guess or to find out what is the average excitation energy in the initial fragment, and then you go from there. So it's possible because you can measure how many neutrons on average came from each of the two fragments. You can measure how many neutrons on average comes as a function of the mass number of the fragment, right? And what you get is this, we saw it before, and this is kind of totally surprising, I think, data, because it goes up and down and up, and it's called a sawtooth. Also, it goes back up here maybe. This is just two experiments, there are many others. They all look like this, and this is, at first you say, why in the world is that? And what you should remember is that you have some excitation energy available at scission, right? You subtract out the kinetic energy, what's left is the excitation energy, and it has now to be divided upon the two fragments, and after you have the excitation, you get the neutron multiplicity. So from this kind of structure, you can also conclude that the amount of excitation energy in the fragment doesn't go in a simple way with mass number. It also goes up and down. So this is kind of strange. Why doesn't the energy just divide according to the mass, for example? That's what you would expect, the heat capacity, right? You just divide according to mass. Why not? Let us see what one would really expect. So here I go back now to my introduction. You remember that we start with a hot compound nucleus. It undergoes a stochastic evolution governed by level densities. It's a kind of statistical process, and in the end you come down to some scission configuration where you have a light and a heavy partner. And you have then, from the configuration, you can figure out how much kinetic energy is taken out, you have some excitation energy left, and it has to be divided. And what would you expect? Well, the simplest thing to expect is, of course, that the excitation energy is divided statistically, because this whole process is statistical. So statistical means you have a density of states in one, you have a density of states in the other, it's divided in proportion to those two density of states. This is the most neutral assumption it seems one could have. But the point is now that these densities of states, they are rather complicated. They are not just proportional to the volume, because they depend on the structure of the levels inside the nucleus, so they depend on the shapes in a complicated way, and therefore it could become complicated. Now, the formalism is simple. If you have a level density for one fragment or you have for the other, the joint probability is just the product with the delta function to take care that the combined excitation energy should be what you have available. And if you integrate over one of them, you can get the distribution of the excitation energy in the other, right? Just the product of the level density in the heavy and the level density in the light at the complementary energy, right? This is, and then you can try to use that. So what kind of level densities are there? Well, the simplest calculation is to take what we call a macroscopic level density. This is typically a Fermi gas level density. And it is very simple because it only depends on the excitation energy in the system. It doesn't depend on its shape explicitly. Of course, the excitation energy depends on shape because you have a potential energy, but otherwise not. And then you have probably all seen this formula. The excitation energy in such a nucleus is just T squared times this level density parameter, which is proportional to the mass number. So if you use this, you simply expect that the excitation energy is divided according to mass, right? This is why it was so surprising. On the other hand, if you take account of nuclear structure, use a microscopic level density. It depends explicitly on shape because it depends on the level, individual levels in the nucleus. And they have, as you know, they are bunched, they have gaps and bunchings and so on. So you change the shape, you change the level spectra, and then you get a different number of states available. So, and this can be calculated. There is a method developed for that. You do all kind of multi-quasi-particle excitations in the nucleus. You calculate pairing. For each one of them, you add collective rotation and you bin it. And then you get the microscopic level density you can use. And you will now see how this can kind of explain why the sawtooth is there. Here's an example. If we now take a typical split close to tin 132 here, and then the partner, which is smaller and deformed, you see how it's completely out of whack. If you divide according to mass, you get the purple arrow here. If you do the macroscopic Fermi gas, it's then centered around this one, but there's of course a distribution, it's a finite system, but it will go like this. And this is not at all what the system likes to do. It really likes to do the excitation in the light one and not in the heavy. And this is because the heavy nucleus here, it's very close to a magic nucleus, double magic even. So there are not hardly any levels, so there is not any level density very much in the heavy one. On the other hand, this is a deformed nucleus. It has lots of levels, so it has very high level density. So you would expect to populate, the energy distribution would be like this, so much more in the light one that its fair share would have been, right? And here you see how it goes with energy. Now we heat up the system, go from 10 to 20 to 40. Then these structure effects should disappear. You see how they do disappear at 40 MeV. You're practically to the macroscopic Fermi gas distribution. And I'll show you one other example. This is this one didn't have so much mass asymmetry. This one has a more extreme mass asymmetry, and you can see this one here. All the energy practically goes into, all of it goes into the heavy one. The light one gets nothing at all at these low energies, and it gets more than just its fair share, right? You can see here. Then as you heat up again, you approach what you would expect just on the basis of masses. All right, so there's a lot of structure to be expected, and now you do all of this, you do the calculations with the shape coming down to the scission configuration. For each scission configuration, there are two shapes. You calculate the level densities and all of this for these shapes and put it in and add it up. And in the end, you get the blue diamonds here. Well, one more thing you do with after the excitation energy, you do evaporation on each of the fragments, you get neutrons, right? And then the mean number of neutrons you get somehow like this. So I should add that this is a calculation in some paper, I don't show it here, but it's an approximate calculation because in fact for each mass fragmentation there's only one scission configuration, namely a typical one, just to make it easier. So this could change this around. But you see, you see here, for example, this one here, 130 that we looked at, doesn't have very much level density, therefore doesn't get very much excitation, doesn't get very many neutrons. Whereas it's opposite there for the partner. And you can see how it is for the more extreme mass asymmetry. So you can link the behavior of this sawtooth of the neutrons to basically to the level densities of the shapes. And this tells you something then about the shapes. Because for example, this one here, it has a shell effect that's plus 6 MeV. This, normally in nuclei you have a negative shell effect, but you can also get a positive shell effect. For the fragment that's created at scission, but that fragment is distorted relative to its equilibrium shape. Its equilibrium shape has minus 7 MeV, so it's way off equilibrium, and this information here tells us something about that. If you were to put in just the equilibrium deformations, you would never get the sawtooth. So this is very important, very powerful, I think, means to learn something about this. A few more, and then I think I'm done with this. So here we try to just do energy dependence, thermal, more or less what you saw, go up to 5.5 where there was data. See, it looks also pretty good. I asked them to also do it 14. I imagine people had measured at 14, but they haven't. But here's how it is practically wiped out. The dashed one is what sort of a rough Fermi gas would give. So this is what you get. And finally, one more thing. if you were to read off how the mean neutron multiplicity goes as a function of the incident neutron energy, you also get some kind of strange behavior for each particular fragmentation, or each particular fragment. Of course it goes up, but it goes up for the 108, there it goes up fairly, and then it goes a little bit. The other one goes up and then up and down. So the way these neutron multiplicities increase also is reflective of the level structure, therefore the shape of the fragment at scission, right? So this is also something that can be easily measured. So the bottom line here is that the neutron multiplicity measurements, they are sensitive to structure effects, including those that are associated with the distorted shapes of the fission fragments at scission. So with this, I will take a break, brief break. Yeah.
So, can you go back 2 slides?
Yes, I can. Which one?
Because, the one that you show the sawtooth of the calculation and the experiments, because it seems that the model, no, the one where you have a lot of experimental data and just
Here. Oh, sorry. So I'm looking at the wrong picture here.
No,
Sorry.
no.
Yeah, I'm looking at
It
the.
looks
Yeah.
like your model predicts exactly the opposite as the
What?
experiments. Like there's more neutron.
Well, no. Well, I mean, it's not perfect, right? I'm not saying that this calculation is perfect because it's not a complete calculation. It's a rough calculation. And my point here is not so much to advance this particular work. It is to say the neutrons, they have this information in them. So let's see here. We have a minimum in the data here, right? I think we have a minimum in the calculation here. We have a sort of, I don't know if we have a maximum. One goes up, but most of the others go down. So we have a maximum here in the calculation here also. And here, so we have a kind of a maximum here. That one it goes like this, right? This is kind of described. Then you come down here, and that also, I think, follows pretty well. So I don't think you can say it's the opposite.
No, I mean, that because in the experiment it looks like the light one emits more, but in your calculation it looks like the heavy one emits more.
No, I mean it goes up and down, right? I mean over here the heavy one emits more, and then here the heavy one emits less, right? And so on. So I don't understand what. What?
Ratio between the big heights.
Yeah, but what is it you want to compare? This one is the partner for this one is this one, yeah. Right, so this one here, if you look at the experiment, you're down here, and if you look at it, you're up here, right? And now you want to say, okay, let's compare the calculation for the same split. Is that what you're saying? And it's lower and higher, but not at all as much. That's for sure. Is that what you're saying? Yeah.
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 I have a question on slide 34. You were talking about the shape. So your excitation energy is divided independent of the density of state, which depends on the shape. But the shape at which stage? Do you consider the shape at saddle, at scission?
No, this is what I tried to explain n times. You come with the system undergoes a shape evolution until scission, where you split. And this is what we're looking at scission. The important thing is how are things distributed when there's no longer, just when it splits. So we're looking at scission. So
the split of excitation energy could happen before, no?
yeah, of course there's a split before, but it can change. It changes all the time as you keep evolving. There's no point reading it off until it stops, right? After you split, then it has stopped. So we could, of course, with this method, if you were looking at before scission, if you could still divide it into two, it's a little bit more complicated when it hasn't actually split. But then you could also say what is the distribution of excitation energy. But it's only necessary at scission is also cleaner because there you actually have two systems, right?
User question? Just for the mini break and. Okay, so maybe mini break and then we come back.
All right. Okay, I will start. So again, I look up in Wikipedia what a photon is. And it has some similarity with a neutron is that it also has 0 charge. But it has no mass, it has electromagnetic interaction, not strong interaction, and it is a boson, not a fermion. And has spin 1. And as you know, with the spin for the photon, it's always directed along the motion. So either along the motion or opposite. This is called the helicity. It's a +1 or -1. This will be of some importance. So what I told you about is that we come in after scission and we have distribution of angular momentum and excitation energy in the fragments like this, and now we do neutron evaporation and we wind up with a distribution like this. Here it's blown up here. Here is drawn a little bit by hand, the so-called Euros line. Let me just say that if we had a excitation energy is way above the separation energy, then the width for neutron emission is much higher than the width for gamma emission, so the neutron evaporation dominates. And of course, if the excitation energy is below the separation energy, you don't get any neutrons. So in the fire simulations, we just simply assume that neutrons dominate as long as you can emit neutrons. This becomes increasingly incorrect when you approach the threshold, because when the gamma for the neutrons goes to 0, there is still a gamma for the gamma here, and even though it's small, it becomes finally important. So you can emit gammas before you exhaust the evaporation, but this is not taken into account here. Now, I just wonder, just as for fun here, the Euros line, I think you probably all know what it is. Does anybody know what it means? Euros, what does it mean, Euros? Somebody has an idea, yes? It's a little bit in that direction. It is superlative of a Swedish word, yr. Yr means dizzy. In Danish it is ør, so yr. And what has that got to do with this? Because Keegan defined Euros line as the lowest possible state you could have at a given angular momentum. This is kind of correct, but you can look at it in the opposite way, and this is what people did in those days. You have a nucleus with a certain excitation energy, and now you ask, how much can it rotate at that excitation energy? And then you go out here to here, and then you're obviously most dizzy when you get out there, right? So this is the Euros state, the most dizzy state you can have at the given excitation energy in the nucleus. Euros, that's what it means, okay? And tonight, if dinner lives up to expectation, we can all try that. Here's just out of free air, drawn a typical de-excitation cascade. Key can also show, so you start somewhere up here, and there are kind of two stages. First, you have statistical emission of dipoles, typically. A number of those, they are typically higher energy than the collective. Once you do this, until you have no statistical excitation left, you are down here at the rotational band, the Euros line, and then you do collective here. So these are mostly electric dipoles, and these, which are associated with rotational bands, are electric quadrupole. And they're quite different, and I will speak mostly about these because they have proven to be very useful for diagnostics. So just a little bit of the kind of theory. You have different multipolarities. You can have monopole, dipole transitions, and so on. You can also have magnetic multipole transitions. M1, for example, plays a role. I'm not going to talk about that. Generally speaking, we know the angular distribution of such a multipole transition. It's given relative to the angle relative to the spin direction of the nucleus. I'm sorry, what? Okay.
Sorry, it's a really nice question at the end.
What?
On the Euros line,
yeah.
Why do you transfer always more moment, more spin with gamma than neutron? It seems so. Like you
Why you say why the E2 have more?
Go, like,
Yeah, right. Yes, I will explain. The basic angular distributions are given in terms of something called the Wigner functions. Never mind, you should probably know what they are, but you can look them up. And the angle is the direction of the photon relative to the direction of the spin. And then it has the lambda, this is the multipolarity, but it also has two indices here. The mu is like the normal mu. It is the component of the let's see one here. Yeah, this is the component of the angular momentum of the photon. The photon has an angular momentum. It's component along the spin. So that's mu. That's familiar. The other one, the h, that's the helicity. So that's the projection of the photon angular momentum onto its axis, right? So it has two indices here, and you can generally write the angular distribution in terms of Legendre, the angle here again, the gamma direction versus the spin direction. That's how it is given. This is of course not how you measure it, because you don't know the spin direction. But let me just give a few formulas and then move on to the E2. Just to show you that there are three different E1 transitions. You can have mu equal to +1, to 0, and to -1. And I should also sort of as an aside say something that's very important for the dipole emission is that you have a collective resonance in the nucleus, neutrons against protons, called a giant dipole resonance. And that one, of course, feeds into the emission of these here, so that must be taken into account. This first one is called stretched. This is where mu has the maximum value. This means the dipole photon takes out maximum angular momentum it can, which is 1 unit, right? Then the angular momentum of the nucleus goes down 1 unit. You could also take out nothing, or you could actually do the other way. And here are different angular distributions. You see here that if you have the nucleus with a spin pointing up, and then you have a positive helicity photon, it tends to go up in on the northern hemisphere, because, you know, to go like this. So you can see this in the angular distribution of these here, that they are in the northern hemisphere. Vice versa, if the photon comes out the lower hemisphere, it has preferentially negative helicity. That's the red one over here. You can see the middle one here just sits around the crater. Right. So you can play on this in various ways, but I'm not going to go into that. Now I'm going to go to the so the dipole transition. Each one can take at most out 1 unit. Right. But it can also take 0, it can also take plus, and it's a bit a question of the level densities. The level densities favor that it takes out something, but it can easily go, because temperature is high, you can go various ways. This is in my drawing, some of them went straight down and some of them went to the left. I think the experimentalists who know a lot more about this, they tend to say that on the average they take out 1 unit. And I think that's what we find with fire also. So now with the E2, then they can maximally take out 2 units of angular momentum. And those that are important are the stretched ones. They're the ones that come in when you have collective rotation, then you take out 2 units. So the index over here, the mu, is +2. So it's the square of the Wigner function has a certain thing, and it has distributions like this. It's again the same. If the helicity is positive, you like to go above the equator, and otherwise you want to go below the equator. On the average, it looks like the dot dashed here. So on the average, the angular distribution from these is concentrated around the equator, right? Because you don't measure helicity, unfortunately, yet. So now, what are they good for? And they are really good for quite a number of things. And the reason is that these collective rotational bands, they are rather well known. These, you know, with the states and the energies and so on in lots of nuclei. So when you come down here and hit the first one and then you go this way here, there is a well-defined, well-known energy here. So for looking, measuring these energies, which you can do really rather accurately, it's like getting a fingerprint of a nucleus. Each one is a fingerprint, in fact, so you get a fingerprint for each of several fingers. So you can really identify the nucleus rather precisely. This is a powerful means experimentally to know what fragment you're dealing with. Here's an example I just took out of the table of isotopes, 2 different isotopes of ytterbium, and you can see they look similar, 0, so on, up, 0, 2, 4, and so on, but the energies are sufficiently different that you can easily tell the difference. So experimentally, you can look at the gammas and then you know which nucleus you're dealing with. Now, you can use this to get information about how the spin magnitude in the nucleus depends on the mass of the nucleus. And I want to just quickly go over some method that, as far as I understand, is called the Manchester method. I became aware of it in the recent Nature paper by Wilson and company. So the idea is there that you measure these transitions here, so you have an intensity from one level down to the next level, the due. And then, of course, if once you get in here, you go down. So the next intensity is just equal to the intensity above, plus whatever comes in from the E1s, the side feeding here, right? And this means if you subtract, then you can find out what the average spin magnitude is by just averaging here over the side feeding, right? The side feeding is the difference between the intensity here and the intensity here. Just so you know with the side feeding that you got into this, and so you know how much the angular momentum was, plus you have to do its correction from whatever was taken out by the E1s, which they say is about 1. So then you can measure the spin magnitudes. So that's very simple. It at least sounds simple to me. It's probably a lot of work. And here's what they get. So this was kind of quite a remarkable result that came out in Nature recently. So as a function of the fragment mass number, you have for 3 different cases the average spin magnitude. And they have here, and they have here. You don't have so many rotational nuclei here, so you can't see anything there with this method, but you get something like this. And this is a little reminiscent of the sawtooth we saw before, right? It's also not sort of a gentle up and down and up. So, and in fact, the two are related. And I want to show you this over here. So we took a look at that, and we say, okay, we have this sawtooth in the Newton multiplicity, which we used to extract the average excitation energy at scission. And then if we now say that just like the energy is distributed statistically, the angular momentum is populated statistically. Why not? Everything's statistical. So if you have a statistical population of the rotational states, then the mean magnitude of the angular momentum is just the square root of the temperature at the moment of inertia, and you put this in, you get the blue here. And we can do it here in the middle and then up here. So this looks sort of rather, I would say, plausible that there is something to that. I mean, that is, you can kind of understand this behavior in the same context as we could understand the thing with the energy division and so on. So, all right, enough about that one. Now there is the experimental problem, as I mentioned, that you measure, I mean, the basic angular distribution is known relative to the spin, but you measure relative to the direction of the fragment. So what do you do with that? And this is just a simple mathematical thing, you probably know about it. So here is the spin, and here is the velocity of the fragment, and this is the gamma f is the angle here. So you also have a, so you can do Legendre representation in terms of this angle, you can do in terms of that angle. The coefficients are different, but if you average over the transverse direction here, then you can get a simple relationship. So this way you can actually predict what the distribution should be relative to the direction of motion. So let me see that. So this kind of a little bit historical experiment by Wilhelmi a long time ago. He's presently here. He did this as a postdoc in Berkeley. So it's the same technique. You identify the nuclei by the E2 transitions, and the basic angular distribution of the E2 is like this. And if you now want to observe relative to the spin direction, you get something depending on now what is the direction of the spin. If the spin is the same direction as you are moving, there is no difference, right? So if the spin is parallel to the fragment motion, you get this distribution. On the other hand, if the spin is perpendicular, then you have to average all around, and then you get that other formula I showed you, you get this. You see it's quite different, there are plus and minus here. So they look very different, and I'll try to illustrate this here. So if the spin is parallel, you get a kind of an oblate distribution. It means a 90-degree peaking, and if it is perpendicular, then you get a forward-backward peaking of the angular distribution. So you just go and measure the angular distribution of those collective gammas, and it doesn't matter which collective ones, they all do the same thing. So in that sense, the statistics becomes good. And Here is, the two opposite scenarios. The red one where it's parallel, as I said, peaked at 90, and the other, peaked at equator, and the other one is peaked forward, backward, right? And here's then their paper a long time ago. They did it, and here's what they got on the right, here like this. So they measure the angular distribution as a function of angle. And here again the two reference scenarios with parallel and perpendicular, and what you should make up your mind is this curve here, does it look more like the green or like the red curve? And I think to most of you it will certainly look most like the green curve rather than the red curve. So this led them to conclude that the observations is consistent with the fragment spins being aligned in a plane perpendicular to the direction of motion. So this is a very important experiment. It says that the angular momentum of the fragments is not randomly oriented in all over, it's perpendicular to the direction of motion. So of course, it was a long time ago, the data is not all that great, so one could say how perpendicular, relatively perpendicular, but how perpendicular. I want to say a little bit about that, and therefore I need to introduce you a little bit to angular momentum, because there are many angular momenta. You have two fragments, each one has a three-dimensional angular momentum. So there are lots of things to keep track of, and a simple way to think about it is if you write down the rotational Hamiltonian, right? Rotational energy for the light fragment, rotational energy for the heavy fragment, the thing that comes from the orbital motion. You can diagonalize this, write it, and you can write it in terms of an overall rigid rotation and then some internal modes that's called wriggling, bending, twisting, and tilting. And they are illustrated here. Wriggling is was already trying to illustrate this. The two fragments do like this. The spins are perpendicular to the direction of motion and they're parallel. And bending is the opposite. They're perpendicular, but so these are the two that Wilhelm says are the dominant ones, and twisting is if they're along and the tilting is if they are parallel also along the spin here. So these are the different modes, and this one's doubly degenerate up here because there are two transverse directions. You have 6 altogether. So now the reason for measuring these things is that different models and different mechanisms, they give different population of these modes. So if we can measure them, we can learn something about what is really going on dynamically. And first of all, the tilting you can forget about because it mostly comes in if you have some significant overall rotation, and you don't in fission. And Wilhelm has showed us that there's not very much twisting, but how little is the question I want to address in a moment. And then later, So we try to make some simulations where we try that's the beauty of the FIRE, we can put in what we want in terms of how much tilting or not, and then see what we get. And here is a result for the yield. The yield at 0 relative to the yield at 90, that's the ratio. This is what I showed you before, if we have only perpendicular. And now if you mix in twisting, this means angular momentum component along the beam, along the fragment direction, they're no longer 90 degrees, but less. Then you get Then you get more and more at 90 degrees, right? So then this ratio goes down, goes like this. And for reasons I won't get into, our best guess is that maybe nature lies here. So the question is this something one could see experimentally? And it seems to me, with modern days, better equipment, more accurate data, one should be able to see if one lies here, if one lies there, or wherever one lies. And if you do that, then you will know how much twisting there is. And this will be a very significant thing in the field. So here's an opportunity for you to become famous. All right. So now back to this. What about these transverse modes, perpendicular modes there that are the dominant ones? Which one is the most dominant? Are they equally dominant or what? We don't know, and the different models say different things. So that would be really wonderful to know about. And this turns out to be possible in principle, but maybe not so easy in practice. Let me explain about that as the last thing I want to say. So, what is the relative orientation of the two spins? You see, if you have only wriggling, they are aligned parallel. If you're only bending, they're opposite. So by measuring the distribution of the relative orientation, you can sort this out. And you can do that if you could measure the helicity of the photon. This means whether it goes like this or it goes sort of backwards. We are not able to do that yet. But helicity is a physical quantity, so I think sooner or later somebody will figure out how to do it. And then we can do it. Let me just finish by just showing you the power of helicity measurements. So here are the two fragments. They emit, each one emits a photon. We have a relative angle between the two photons, and now we look at the distribution of that angle. For example, two photons that have the same helicity. Then, if the two spins are parallel, as I explained before, then there's a tendency for the photons to go up. They go more in the same hemisphere as the spin, and this means the opening angle is not so big. On the other hand, and you see that here, here's a simulation. Here, this is the two schematic scenarios, if it's precisely parallel, if it's precisely anti-parallel, and this is then, again, a fire simulation where you take into account all the de-alignment from the neutron emissions and the E1 and so on, and as you can see, it doesn't do all that much. So you get a forward peaking, right, of the forward peaking at 0 degrees. And vice versa, if the two spins are opposite, the two same helicity photons will tend to go opposite, and you then get a distribution that peaks at 180. So, if you can measure helicity, you can see there's a huge difference between these scenarios. You should be able to measure this distribution, and then you can tell. So, this is another opportunity, but this is an opportunity that, contrary to this one, that is a now opportunity, you can do it. This one here is whenever the proper detector has been developed. So this should be an incentive to you to go to your detector friends and tell them to please think about this. Then you can determine this. And I think without that, I'm not so sure how easy it's going to be to determine wriggling versus bending. Then the theorists can just keep fighting over it. So that is basically, I think, the finish of this. I remind you of the other opportunities to come and talk about it at lunch over at the bagel shop. And we have still time now for a little bit of discussion. Thank you.
Yes, thank you.
Any questions, comments before wanting to take on this opportunity?
Why can't you infer all of this angular momentum with your neutron spectrum?
I'm sorry?
Why photons are better to infer the angular momentum of a fragment than the neutrons?
As you saw, the neutrons do not carry away very much angular momentum.
Mm-hmm.
So it seems it's, yeah, I'm not sure how you would. They don't seem so suitable, right? They tend more to cool the system, but leave the angular momentum alone. On average, right? Yeah.
Can you elaborate more on the opportunity? The first one that you said.
Yeah.
Is the idea to tag a fission product?
Yeah.
Measure the angle.
Yeah. So you know, so you need one detector, I think, only, right? One detector. Yeah. No, you need one detector for the gamma, or then for you need to know where the fragment goes, right? The product goes, and then you need to know where the photon goes, right? These two things you need to measure, and then you need to measure the energy of the photon carefully, because you have to find out that it's one of these rotational E2 photons. But the beauty of it is that there are many of those, and they all add up. So you don't have to just get one. You can take 20 different ones. They all add up because they're all aligned in the same way. So that makes it kind of better. So you don't really need all that much, I think, fancy equipment.
How do you know that the neutrons are not carrying the
Yeah. That's of course. How do we know? There's all this thing about theory and experiment, right? With the theory or modeling or calculation, you make some predictions, and then you make some experiments, And if there's a discrepancy, well, then you know there was something wrong. Well, it's not a working experiment, but most likely something wrong with your assumptions about this, right? So I will know if you find a huge discrepancy between what is calculated and not. I think it's. I mean, it's not so directly. And in fact, I didn't mention this, but I was going to mention it. It's not a settled thing how much angular momentum the neutron carries off. I showed you a very simple sort of classical estimate, essentially. But there are other more advanced ways to calculate neutron emission. And if I understand right, I mean, from Ionel there has tried to do that. He gets more. So this is not a settled question, right? So I am showing you what you get with this, and so we need the data to try to sort this out.
Thank you.
So I know you said this already, but could you repeat the argument as to how I think it's the E2s allow you to identify the fragment?
Yeah, right. Yeah.
You said it's like a unique fingerprint.
Yeah, right. Exactly. Yeah. Well, I mean, you have an energy. You measure the energy of the photon, and according to Dorothea, I just spoke with the other day, I asked her actually. She said that you can measure these energies down to one here. I mean, where was my down to 1 kV? I think she said. Right? Where are we? I had this. Where comes it now? Here we are. Right. You can measure to an accuracy of 1 kV. I think she told me. So you can see here, for example, these two. You take number 4 is 260 and 253, so they are sufficiently apart. I mean, you should take differences, right? Differences between these. And all these differences you know ahead of time. This is in the table of isotopes. And then you measure, right? So then you can see. There are occasionally you can get by chance. I mean, these are not the typical fission fragments. I just looked in the table of isotopes randomly. So I also randomly looked at 172 erbium. This is because this one here you add 2 neutrons. Then I try to add 2 protons, but that doesn't work because they don't have data on that. Then I subtracted 2 protons, got 172 erbium, and that one is practically identical to this one. Yeah, this was very surprising. This happens rarely. So it's not all you can do, but there are many you can do. 20, 30 or something, where typical fission fragments where you have unique information. And also, it's extra safety that you get a whole, typically you get a whole sequence of, so get just not 1 fingerprint, but 2, 3 fingerprints. So if it doesn't match, something is wrong, right? So you can do this, I think, I'm not an experimentalist, but my impression is you can do this in a relatively reliable way.
If I can comment on top of this,
Yeah.
because that's a very good example of what Nicola was mentioning. This is the nuclear structure information, and we don't know that from theory. We use that from the experiment. And if we don't have the experiment, we don't predict any of the gamma lines, the 2+, 2, 0+, etc. So that will be missing the gamma predictions, because we don't know that. We use experimental data.
Yeah.
Just a very short comment of the course. Theoretically, it sounds very nice. In practice, you have to consider that these are very short-lived products, and you have a lot of fission products, so it's not so easy to find the gamma lines.
Then I go back to the neutrons, if that's okay. In your thermic gas model, it works quite well. Do you expect to see any like pairing effect, or do you include pairing effect?
Yeah, pairing, right. You are typically in the fragments that have, I don't know, 10, 15 MeV excitation. So certainly the model assumes that the neutrons there that have high enough energy they can get out, they are no longer paired, right? They are individual nucleons. And it's basically, it's a Fermi-Dirac distribution, but that high above, it's just a Maxwellian distribution, right? So that's the assumption, and that's really all I can say. I mean, I'm amazed how well it works, because I just thought of it out of the air. I didn't know anything about Weisskopf or something. The other people told me that later. It works so well, and it works well enough for our purpose that I did not go into. I don't consider myself an expert in the neutron emission or photon emission for that matter, more in the dynamicals, the properties of the fission. So maybe somebody knows, I mean, I don't know precisely.
Okay, so maybe we can conclude this session. Thank you again.